I'm here to talk about cloud-based per title encoding capabilities. I've got an ongoing study that I'll reference very late at the end of this presentation, but it's something that I've been looking at for 3 or 4 years, and something, everybody loves to talk about new codecs, but I think the per title gives us a lot of the same benefit as new codecs with a lot less implementation hassle. So I'll start out talking about what I mean by per title, then I'll look at the common features of some of the cloud-based encoding tools, and then I'll talk about how you can compare technologies back in your own space, and a couple things about what I'm doing in the study that I just mentioned. Let me say that my study is open to all cloud-based per title facilities. I know ATEM has a great per title encoding engine. I'm not sure that's available in the cloud, so that's not something I would look at. I'm really more focusing on the types of tools that are available to anybody on a pay-as-you-go basis. So AWS has them, Brightcove has them, Microsoft Azure has them. Those are the services and the tools I'm looking at. Anybody out there who's got their own set that meets those requirements, then just get in touch and I can consider including that as well. So what I mean by per title, you upload a file, the service gauges the complexity of that file, usually using something like CRF, or if it's an expensive service, it uses artificial intelligence. And then it creates a unique ladder that's unique in terms of perhaps the number of rungs, the maximum data rate, and then the individual resolutions of those rungs. So if we upload Big Buck Bunny, we may get an encoding ladder that's, it's 1080p at the start, drops down to 640 by 360. It's got a 1.8 megabit per second top rate, a VMF score of 95. And it has 5 rungs. But if we upload a football game, American football, for VOD viewing, we see the same technology might produce an encoding ladder that's got 7 rungs with a 6 megabit per second top rate. But the key thing in here is that the quality up here is 95, the quality down here is 95 as well. And so you want, even though you're sending very disparate files into the cloud, you want similar top rung quality. And I focus on top rung a lot because that's typically the only rung that's going to be very comparable from technology to technology. Some technologies are going to go lower resolution very quickly. Some will maintain higher resolutions. And the other thing about the top rung is that it's probably the rung that in most services is used the most. So I look a lot at top rung quality. And the benefits of per title are bandwidth saving for easy to encode clip like Big Buck Bunny, quality improvements for hard to encode clips if you let your per title technology go higher than normal. And then in the middle of the encoding ladder, you should be able to produce better quality at the same bit rate, which most people would consider a quality of experience improvement. So what are the common features in the per title cloud-based services that I'm looking at? All of them, you upload the file, and then most of them give you the ability to choose a minimum bit rate, a maximum bit rate, maximum resolution, maximum or minimum resolution, and then a minimum number of rungs and a maximum number of rungs. So if you're going to set the maximum bit rate at 6 megabits per second, you might as well set the maximum rungs at, say, 6 or 7, because you really don't need more rungs than that to get good distribution within the encoding ladder for easy switchability. I put quality in red because not all services allow you to adjust quality. And it's either going to be important or not important. The services that I've checked with AWS, they don't let you impact quality, but they have a pretty good measure of achieving a quality score between 93 and 95, and we'll talk about why that's important in a moment. And then the services that I'm looking at now, or services that I've looked at now or have looked at in the past include Bitmove and AWS. And with AWS, I should mention that we're looking at auto ABR, not QVBR, which allows you to upload a ladder and adjust the bit rates within the ladder, but you can't create a unique ladder with QVBR, and you can't change the encoding resolution. QVBR works great for live content, but it's not so good for VOD, and that's why AWS introduced auto ABR. And then Azure, Tencent, and Encoder, Brightcove all have per title capabilities, as I described a few slides ago. So how do you choose the best option? You start with your existing scenario, and in some cases that'll be a fixed encoding ladder. In some cases that'll be your own version of per title encoding. And you start with X test files. I'm testing 23 in my service, and you start with your existing encoding ladder and your existing quality measurement. Then you test with however many services you want to test with, And then you compare, 4 aspects: cost, per title performance, overall quality, and the impact on streaming bandwidth and quality of experience. And we'll go through all these alternatives for the remainder of the presentation. So when I talk about cost measures, we're looking at extra encoding charges associated with using the service. So with AWS Elemental, you've got to use the top quality encoding level, which is going to cost you more than even 2-pass VBR. With BitMove, and there's, I think, a 1.5 to 1.25 to 1.5 extra charge because you're using per title. And that makes sense because there typically is going to be an analysis pass that's going to cost the service money to perform. So you want to understand it in your comparison what the extra charge is going to be for using per title. Then you're going to look at how many additional rungs does the service create, how much additional storage does the service create, and then how much additional streaming bandwidth will it either save or add to your current streaming cost. And then all of these are plus minus, right? So if you've got, sometimes it will increase the number of rungs, sometimes it'll decrease the number of rungs. You compute that through all the test files and then sum it up and you see where you are. And the basic analysis is, this is your current ladder, this is your per title ladder. And we see that with the current technology, I've got 6 rungs and the total bit rate of all the files that I've got to store. And typically you've got to store this on the origin server, so it's going to be pretty expensive storage. The per title ladder produces 7 rungs and the total storage is 1.3 or 13 megabytes. So I've got an increase of storage cost in this particular per title technology for this particular test clip of around 7 megabits and 7 megabits per second. Obviously, you want to translate that to actual megabytes, and I've got to produce 1 additional rung in my encoding ladder, and every rung typically costs you money when you produce via cloud encoder. So that's something you want to incorporate into your cost comparison. And then the streaming cost, that's the hardest one. It's a difficult computation, and I put that last, and we'll cover that when we get there in a few minutes. So this tells us on the encoding side, we've got to encode 1 additional rung. We're going to have to store 6.6 megabits per second on the origin server, and then we'll look at how much this is either going to cost or save us in streaming cost, and how much it's going to benefit us in quality or hurt us in quality when we get to the final slides. And then when I talk about per title performance, I look at quality, top line consistency, quality consistency, rung integrity, and then the resolution and data rate selected by the service for the individual rungs in the encoding ladder. And then Jan went into some of this, with VMAF, which is the quality metric that I use in most of the studies these days, primarily because it's got valuable things like, the ability to say, okay, 93 quality according to this white paper by Risa Rasul, who's a CTO of Real Networks. If you've got a score of 93, it pretty much means that the file is either indistinguishable or it's got noticeable but not annoying distortion. Basically, from my perspective, when I'm producing an encoding ladder for a client or for experimentation, I'm going to target between 93 and 95 because scores above 95 aren't going to deliver any perceptible benefit to the user or to the viewer. And as Jan talked about, a score of 6 is just noticeable difference. So if I see a variation in BMAP score of 0.5 point to 1 point, I think it's irrelevant. If it's 12 points, it's holy cow, that's going to be noticeable to most viewers. And then again, what's this mean? It means that when you're looking at the top rung, or any rungs actually, a difference of between 93 and 95 isn't going to be noticeable. On the other hand, if you've got a per title technology that improves the top line VMAF score from 95 to 99, then you should be thinking, well, gosh, nobody's going to notice that. So whatever additional bandwidth that costs me to do is going to be wasted bandwidth. And this takes us back to the slide that we were looking at a few moments ago, where we looked at the storage and the number of rungs. And here we see that the top rung data rate increased from 2,600 to 5.4 megabits per second, which is an increase of 2.8 megabits per second, 109%. And it improved the VMAF by 0.46. And we know for 2 reasons that's irrelevant. Number one, we're improving from 95.15 to 95.62, which is over the 95 or 93 to 95 threshold. And second, we know it's not anywhere close to 6 VMAF points. So nobody's going to notice this difference. And then And then, so that's, VMAP measures overall quality, and I like to go beyond that for a couple of reasons. And the basic question here is you're looking at two streams, and this is the Moscow State University Video Quality Measurement Tool. And this is one of the visualization screens that lets you see the VMAP score of two files, one in red, one in green, over the duration of the file. So you're seeing the VMAP vary significantly, and you're seeing in particular that the red score has a lot more deep down spikes that indicate regions that may be visible to viewers. Now, in this case, these are very tiny spikes, maybe 1 or 2 frames, so they may or may not be, but it's something that you want to measure. You don't want to look at only the top line score. So if I was only looking at the top line score for the red file, I would say, well, gosh, it's 95.02, that's fine. On the other hand, I also look at the 99th percentile score, which means what score are 99 percentile of these frames over? And in this case, it's 86.36. And I want to look at the low frame score because the low frame is, even though it's only 1 or 2 frames in 1 or 2 regions in this file, it may be significant enough that it will be visible to a viewer and it could really degrade quality of experience. So, when you're in the business of choosing a per title encoding technology, you want to put yourself in the brain of that per title engine and say, which stream would I choose if I could do this manually? All these are automated systems. You don't have that option. But when you're choosing between the technologies, you don't want to just look at the top score and say, well, gosh, VMAF 95 is fine. You also want to look at other things like the 99th percentile and the low frame. And in this case, the green technology delivered a file that was 34 kilobits for 3,400 kilobits per second, and the VMAP score is slightly higher. Don't really want to focus on that, but we see that the 99 percentile is 3 VMAP points higher, and low frame is also 3. So these are not dramatic differences, but you can look at the frame graph here and say, there's a lot fewer green downward spikes. And in this case, if I was making this decision manually, I might say, yeah, I prefer to spend the extra bandwidth and get a little bit higher VMAP, but more importantly, get less frame variability and increase that low frame so that fewer viewers would notice the difference. And the difference between the 95 average and the 86 and the 83, that's something that if the frame duration or the downward spike is long enough, then that's something that a viewer could notice. Viewer's not going to notice the difference between 95 and 96.96, probably not even the difference between the 99 and 99 here, although they may see some quality differences in this file that they wouldn't notice here, but they probably would notice a low frame score in probably both of these cases. So I don't like to look at average VMAP when I'm comparing the technologies as the sole measure. I like to look at the 99 percentile score again. What is the value at which 99% of all frames are above, and also the low frame, which for me tells me what the likelihood of a visible transient quality issue might be. So getting back to where we were, the data rate's up 109%. VMAF is pretty much irrelevant. 99 percentile is up 0.28. That's also irrelevant. And here, the low frame is actually down. So this technology increased the data rate by 109%, had minimal impact here, but actually decreased here. And in this case, you would probably reach the conclusion, hey, at least for this file, this technology isn't one that I want to implement. We'll look at all the test cases before we make a decision, but in this case, it certainly wasn't a clear win. And then I like to look at top line accuracy. So these are all the test files that I'm testing and the various tests that I'm running. So it's 23 different content between movie content, sports content, animated content, and then typical office type stuff. And when I look at the data rate, this is interesting. The average bit rate for my existing baseline technology is 2.874 for all of these 23 files, and this is the top rung again. And the average VMAF score is 95.98. And then for this particular per title technology, the bit rate is up pretty significantly. It's up by 700 kilobits per second, and the VMAF score is up only 0.2. So this tells us that my existing encoding technology is more efficient than this per title on an overall basis relating to the top rung, and we'll look at how I quantify that in a moment. But in this case, I'm thinking, okay, well, for my baseline technology, the data rate's lower, the VMAF is about the same, so the overall quality looks good. And I also like to understand the standard deviation. So this is the standard deviation of the VMAF. This is the 99 percentile. This is the low frame. And we see that the standard deviation of the existing technology is only 1.1. And basically, when I implement a percentile technology, I want to make sure that all of the top rung files of all the files that I encode using this technology are going to be pretty similar. I don't want to have a lot of variability in the quality, even if some files are easy to encode, some files are hard to encode. And this tells me with the standard deviation of 1.1, this tells me that there's very little variation in the overall quality of these files. And it's not too terrible with percentile encoding engine number 1. It goes from 1.1 to 1.44. So that actually is not too bad. And then similarly with the 1 percentile or the 99 percentile, here it's 2.17, here it's 2.87, not dramatically different. And in this particular case, as it relates to the low frame score, this percentile technology, it produced a higher bit rate, but it was a little bit more resistant to transient quality issues as defined by the low frame VMAF score. So that's what I look at in terms of consistency. I also want to check the rung integrity. In this case, I want to make sure that the jump between ladders is between 1.5 and 2.0, and that's Apple HLS guidelines back in the Rosetta Stone, TN 2224 days. And basically that's to make sure that there's not too many files compressed in a small space, so that you might switch back and forth and so see no visible difference and encode too many files. And you don't want them too far away, because then you may end up stranding some viewers at lower bit rates, even though if there was a mid bit rate, they could get better quality because they've got sufficient bandwidth. So in this case, this is just a number I measure. All the technologies that I've checked so far, they were all within these parameters, but I've tested technologies before that had a jump, say at 2.2 or 2.5, and that really could strand viewers at lower rung. On the other hand, if you see, 1.3, 1.2, you're probably encoding too many rungs, and because you're paying for each rung, it may not be as efficient a technology as you would like. And then this is a subjective test that we're going to get to in terms of how you could do it mathematically in a moment. But this is SpongeBob SquarePants. This is an animated clip. Animated clips are relatively easy to encode, but you typically want to encode them at larger resolutions lower down in the encoding ladder. So my current technology for 500 kilobits per second actually encodes this particular clip at 720p to get an overall VMAF score of 72. The percentile technology that we're looking at here encodes at 640 by 360, a quarter of the resolution, and gets a VMAF score of 55.71. And that's a difference of around 16 points. And 16 points is something a viewer would notice, even if viewing on a mobile phone or a tablet via 3G or 4G. So, this is a subjective type analysis you'd probably want to do side by side with the different encoding ladders. And with hard to encode clips like football or soccer, sometimes it pays to have lower rungs upper in the encoding ladder, because you get better scores there. But particularly with HEVC, which these tests are done using, and animated clips, it's better to push higher resolutions lower in the encoding ladder, and this is going to make a significant difference depending on how your file is distributed. And let me make that point here, because I think everything we've talked about so far relates to the encoding, not to your distribution pattern. So if your distribution pattern, you're in Scandinavia and everything's IPTV and all you're distributing is the top rung, then these two technologies actually end up looking pretty similar, right? Because 100% of your viewers are watching this frame here. They're going to go from 95.72 to 96.53. Perhaps you're wasting some bandwidth, but the visual experience is not going to be different. Now, if you're distributing this file via mobile, if you go to your server logs and you see, gosh, 50% of the viewers are watching the lowest 3 rungs, then really have to say this type of technology difference is going to make a significant difference to the people who are actually watching our streams. Okay, and then I want to look at pure encoding quality, and we kind of looked at that a few slides ago when we looked at the the average VMAF score and the average bit rate score. But keep in mind that we're looking at two different aspects to encoder here. We're looking at the per title aspect where the encoder is making decision. How hard is this file to encode? What type of content is it? Which resolutions are most effective in the rungs? What's the top data rate supposed to be? All those decisions are totally independent from pure encoding quality. If you have a great decision maker on the per title encoding side, but a very poor encoder, then you're going to have poor output. On the other hand, if you have a great encoder but poor per title encoding decisions, again, you're going to have a bad result. So you really do need both. And it takes us back to where we were a few moments ago in the SpongeBob content. And I like to use VMAF per megabyte. And here what we're seeing is that my current encoder had a bit rate of 2,500 kilobits per second, or better stated 2.5 megabits per second, and produced a VMAF score of 95.72. So that gives me 38.28 VMAF points per megabyte. On the other hand, over here, we have a 96.53 VMAF score, 4.775 bit rate for 20.21 VMAF per megabyte. And that basically tells us that this, irrespective of the per title encoding capabilities, is not as efficient encoder as this. And what about streaming bandwidth or quality? I think that's the most important thing. Everything so far is very straightforward. You don't have to do any complex allocations or any of that type of analysis. But really what you care about with the streaming per title encoding technology is, given my current distribution pattern, given how viewers are actually viewing the rungs in my encoding ladder, what's going to be the impact on streaming bandwidth and what's going to be the impact on VMAF? And to do that, you're going to have to do a weighted average computation. For both the current and per title technologies, you're going to have to compute your encoding ladder on each test clip, allocate the rungs in this to the various bandwidths that people are retrieving from your current files, and then you're going to have to allocate those based upon actual usage. So in this case, we've got 71% of the viewers are actually watching this file, 13% are actually watching this file, and then you compute weighted average scores for bit rate, VMAF, 99 percentile, and low frame, and that tells you that on an average basis, on a per second basis, you're spending 2.38 megabits per second to deliver this clip, and you're delivering a VMAF score of 94.41. And then you do that for your current, you do that for your per title, and then compute the difference. And this is a different allocation. This is more of a mobile type distribution. What we saw before was kind of a top heavy US distribution. But what we're seeing here is that everything's yellow, which means everything's bad. The per title encoding technology cost us on an average basis 394 kilobits per second, but decreased the VMAF by 10.59. Decrease the 99 percentile by around, a little bit lower than 8, and decrease the low frame score by this much. And these are numbers that you can kind of take to the bank. You can say that based upon my current existing distribution patterns, this will be the impact of this particular per title technology on this particular test clip. And that's it. I really haven't nailed down which services I'll be doing yet. I'll be looking at both H.64 and HEVC, and the report should be available in January 2022. Hopefully, I've given you enough to feel like you can do a lot of the analysis yourself, and check back on the Streaming Learning Center website early next year to see if it's something you might be interested in picking up.